Just as we did for the case of Coulomb force and electric field, which is if we had a configuration of charges in space, we said, what if I bring a test particle here? What would be the force acting on that test particle? We said you have to calculate with all the distances and so on. And then what if somebody wanted to bring a different test particle? We say you don't have to repeat the calculation, right? If you're bringing it to the same location, all you have to do is keep this number that we call the electric field at hand, which you have already calculated, and the whatever charge test particle you bring into the room, then the force on that charge will be the electric field times your test charge. That's what we said for the case of the electric field and the Coulomb force. Right? We define the electric field as the force divided by the charge. For electric potential, we're going to do the same thing. And this is the setup. So you have a bunch of particles, Q1, Q2, Q3, and 4, and whatever number you have. And then you bring this test particle here. And you wonder how much is the energy of the system. Right? So the energy of the system when you bring a test particle can be written, as we said, as we calculated before, as the sum of all of the pairs that you can build between the charges, right? But if you call this, if you make a separation between the charges that you're not interested in moving and the charge that you're going to be moving, possibly changing location or magnitude, you call the source charges 1, 2, 3, and 4, then you can separate those terms, which in general are like this, okay, Qi, Qj over Rij. You can separate it in two pieces. The sum of the terms, which is only over the sources, and then you write the terms that include the test charge that you bring into the problem. So those terms would have the form Q test factor of K Q sub I divided by the distance between sub I and the test particle, and you're summing over all of the charges that you call the source charges. Right? The Q test was common to every term that you had there. K, Q1, Q test, K, Q2, Q test. So you bring out the Q test. So notice that this can be written like this. The electric potential energy of the whole system is equal to the electric potential energy of the sources, right, among themselves, plus some quantity, the charge of the test particle that you brought, multiplied by this quantity that we're going to call the potential produced by the sources. So if you ever wanted to, instead of the Q test, figure out what's the energy of the system if you bring a different Q test particle, all you have to do is, well, this term is going to be constant. That's not, you're not changing the source's location, right? This term is also going to be constant. It depends on where you place the test charge, but it doesn't depend on how much is the test charge that you brought, right? So the potential energy of the interaction between the test charge and the sources is given by this term, the test charge multiplied by this quantity that we call the potential. So the picture that we have here, that we have now, is similar to the picture that I told you about the electric field. The picture is, when you have a bunch of particles in space, the space surrounding the bunch of particles acquires a new property. Those charged particles interact with the space surrounding them and modify the space, right? So when you bring some test particle to that space, that test particle interacts with the local space. And that's how it feels that there is some charges located nearby, because the space at the location where you put the test charge has some particular property. In the case of the electric field, we imagine this property as being a little vector, right? And when that vector electric field multiplied by the charge, when you multiply by the charge, it told you directly what was the direction in which the particle would experience a force. Now we're having a picture that is the same, basically the same, except that the quantity that we assign to every point in space is not a vector, it's going to be a number. Because notice that this is a number. There's nothing vector about this quantity. So that quantity is called the electric potential. And it's measuring volts. All right? And if you were to just take two charges, just 1 second, two charges Q and another one Q here, the potential energy of those two charges will be KQQ divided by the distance between them. You can define the potential produced by the big charge Q as just, if this is the test charge, then take U divided by the test charge, and that will be KQ over R. So now, to the space surrounding a charged particle Q, you assign different values. And those values are called the electric potential at that location. And they're simply KQ divided by whatever distance you have between point P and the location of the charge Q that you have.